We are happy to have next Gustav Mogull telling us about gravitational Bremsstrahlung from spinning bodies using a worldline quantum field theory.
Thanks, Justin. And let me also extend my thanks to Gabrielle and the other organizers for this, this very pleasant few weeks. So today I'm going to be telling you about this series of papers which I've been working on with Jan Plefke, Jan Steinhoff, and Gustav Jakobsen, all four of us being based at various subsets of Humboldt University and AEI in Potsdam, myself and Gustav being based at both. And what we have been doing is we've been using this Worldline QFT formalism, which we're now rather fond of, to study the Bremsstrahlung produced when you have a scattering, an unbound scattering of two black holes. And recently, we've now been working on extending this also to include the spinning case. So that's this most recent work, which we're hoping to have out within the next couple of weeks. And essentially, the object that we've been trying to calculate, that we have calculated, is the waveform. So h mu nu, as measured by an observer far away from the point of the scattering. So what the basic plan for my talk is the following. I'm going to start by just saying a few words about the Worldline QFT. So that essentially relates to the first of these three papers, which I originally did with Jan Plefke and Jan Steinhoff. Then I'm going to dive into the second, which is where we used this formalism to obtain the waveform, 2 p.m. order. And then finally, I'm going to tell you about what we've been doing to extend the Worldline QFT to incorporate spin into the formalism, effects up to spin squared, and I'll show you how we've been, we believe we now have a waveform that describes, that works up to spin squared. So to begin with the Worldline QFT formalism, what we do is we start from an action which consists of the usual bulk Einstein-Hilbert action in 4 dimensions. We add a gauge fixing term, the usual harmonic or de Donde gauge fixing term. And then what we do, very similar to what Gregor Kalin and Raphael Porter do, is we, rather than using a pair of scalars to represent our black holes, we simply use a pair of world lines. And this form of the action is, in fact, entirely equivalent to writing what you may be more used to, the more conventional Worldline action. This particular form is related to the Polyakov form. It turns out to be more useful for writing down Finemen rules, as I'll explain in a moment. And the novelty of the Worldline QFT formalism is that not only do we quantize the gravitational field, so h mu nu, the disturbance about the flat space metric, we also quantize z, which is the deflection of the trajectory of our black hole around its original straight line trajectory. So what we do is we think of both of these things as propagating degrees of freedom. So Z and H, they're both going to have propagators, they're both going to have Finemen rules, and they're going to interact with each other. But what's going to make it a little bit interesting is that because this deflection mode lives only on the world line, that means that its Fourier space is going to be energy space rather than momentum space. And when we have Finemen rules which live on the world line, they are only going to conserve energy rather than for momentum. So the idea then, when we start thinking about computing physical quantities, is we derive them as expectation values of operators within this Worldline QFT formalism. So formally, we have a path integral over h mu nu, the graviton, and the individual deflections of these black holes. Now, this is a very formal way of representing it, but as I say, in practice, what this is going to boil down to is working in Fourier space, drawing Feynman diagrams, and having a set of Finemen rules. The real advantage of this perspective, as opposed to, say, using scalars, taking a more conventional QFT approach, as many people have done, is that it is very, very simple to identify the classical limit. From our perspective, there's no need to look at a soft region. To us, the classical limit is identified simply with taking the tree-level diagrams. That's all one needs to do. Sum of tree-level diagrams, discard the loops, that's it. That's really how simple it is. And as I said, today I'm going to focus mostly on the unbound two-body problem, but everything that I say also has relevance to the bound two-body case. As we know, there are mappings between unbound two-body problem and bound two-body problem. This has been explored by Kellen and Porter. Okay, so let me go ahead and start showing you how we can derive some Finemen rules. So as I explained, the basic idea is that we take this deflection of each of the individual black holes from their original straight line trajectories, and we think of them as a propagating degree of freedom. Now, I'm not going to say too much about the Finemen rules which come from the bulk action, because there's nothing really particularly special about them. We have, the usual graviton propagator working with the Donda gauge. We have a free graviton vertex, a full graviton vertex, etc. I think we're all very used to this at this point. Nothing particularly novel there. What's interesting is the Finemen rules which come from the second part of the action, the Worldline part of the action. And the interesting feature here is that because this part of the action is integrated only over time rather than over four-dimensional space-time, that means that any vertex which you derive from this part of the action is only going to conserve energy, not momentum. In some sense, very loosely speaking, the way you can think about this is that, momentum conservation being the result of spatial translation invariance, the presence of these two world lines has in some sense broken that spatial translation invariance. So you only have translation invariance along the world line, so one component, so that's energy modes that you're preserving along that world line. And as I say, you can obtain a propagator for the graviton. You can also obtain a propagator for the world line. So in this case, as you see, we have two time derivatives here. So that gives rise to a 1 over omega squared type propagator, which we're going to have for this deflection mode Z. And we also have a choice of different I epsilon prescriptions that we can use. And this turns out to be quite important. And we can make different choices. However, given that today I'm going to be focusing on radiation, it's going to make most sense for me to focus on a simple retarded prescription for this propagator. And physically, what that means is that we identify the deflection in the far past as 0. So that means that our impact parameter and the velocity of our black holes are identified with the incoming states of the black holes. As I say, this isn't the only choice that we can make, but for thinking about radiation, we believe that it is by far the most convenient. So the propagator is quite straightforward to obtain. What's a little bit more interesting is to obtain the interactions. And the reason that they are a little bit more involved is because you have to untangle the dependence on these deflection modes from the dependence on the metric. So h mu nu on the world line is a function of x, the position of the black hole. And that, of course, depends on the deflection. So you've got to separate those things from each other. And the way we do that is we, again, move into momentum space. So we can write h mu nu as a Fourier transform, where the position is now the full position, the original trajectory plus the deflection. And then what we can do is we can simply do a series expansion of this exponential. Z implicitly contains some higher order powers in G Newton. Essentially what you're doing here is a PM expansion. And then finally, you can take each of these individual deflections and write them as their own individual Fourier transform. And you end up with something which looks like this. And what's going to happen is when we take the full action and when we do an integral over the time, this exponential right here is going to give rise to an energy conservation on the world line. So if we feed this result for h mu nu into the action, we can then start reading off our interaction vertices. And hopefully now it becomes clear why I picked this particular form of the worldline action. What's so convenient about it is because the dependence on the graviton is only ever linear. So you never see more than one of these h mu nus at a time. So what that means is we can actually write down an endpoint expression for the vertex without too much trouble, which I've given right down here. So the simplest vertex is, of course, just the source. So we have the world line represented by this dashed line, which emits a single graviton. And you can simply think of this as the linearized stress energy tensor of the theory. That's probably a very simple explanation. So K is the momentum of the emitted graviton, V is the velocity associated with this world line, and the energy component conserved is K dot V. Similarly, we can then start to read off vertices where we have more and more of these Z's stacked on top of each other. And in this case, the energy conserved is k dot v plus omega, where omega is the energy of this deflection mode. So here we have a mixing. And I emphasize that these dotted lines are not meant to represent fields. They are meant to represent the background, the world line, and they're meant to indicate that these interactions are happening on a line as opposed to in the bulk. That's really all they mean. But because these higher order terms are just coming from the expansion of an exponential, it's really not that difficult to generalize to an endpoint expression for this vertex. So we can obtain all of the Finemen rules from the world line action in a very straightforward fashion. So now we can proceed to go ahead and actually make use of those Finemen rules, which is what I'll do next. So now let's start thinking about the radiation. So the thing that we're going to want to calculate now that we're thinking about radiation is we're going to want to obtain the expectation value of h mu nu in momentum space in the WQFT. And diagrammatically, what that means is we're going to need to take a sum of all the diagrams where we have a single graviton being radiated out. So for instance, the easiest case of that would just be 1 p.m. leading order. And at this case, it's extremely trivial. The black holes don't even talk to each other at this order. And all we need to do is for each black hole is just draw a single diagram. Basically, the world line just radiates a graviton. That's it. It's as simple as that. And essentially, all that this equation is saying is that at leading order, h mu nu is just sourced by the linearized stress energy tensor. So it gets interesting once we proceed to 2 p.m. Subleading order. And in this case, we do actually have the black holes starting to talk to each other. So for instance, we have this diagram right here, where the two black holes exchange a graviton, and then we have one of these deflection modes, which travels along the world line of the first black hole, and finally gives rise to a graviton which is radiated out. So you can see all these features of the rules that I showed you. So we've got free vertices here, which is associated with these free delta functions. Two of them are on the first world line, so it's dotted with V1. The third is on the second, dotted with V2. And then we have two propagators, a graviton propagator and a Z propagator. So the graviton propagator is right here, and the Z propagator is right there. And the energy conserving delta functions allow us to solve for this omega component, which is being transmitted along the world line. But what you notice is that because we're integrating over momentum, but only conserving energy at the vertices, even though this is a tree-level diagram, we're still going to have some integrals left over. We're not going to resolve all of our components of our integration. Similarly, another diagram that we can write down is this one right here, where each of the black holes emits a graviton, and we have a free graviton vertex in the middle. And in this case, the measure looks a little bit different. So we've got a momentum conserving delta function associated with the free graviton vertex. However, you can quite quickly show that these two integral measures can be brought into a common form. Basically, just integrate out omega 1, and then you can reinsert the integral on Q1 in this first guy. So you can bring them under a common integral measure. And of course, the other diagram, which I missed, is the flipped version of this guy. You have the same diagram, but just flipped in a horizontal plane, which you also need to include as well. So that's how we proceed to write down h mu nu. And essentially what we're doing, one way to think about this is, in some sense, we're really just solving the equations of motion. So one perspective which I find quite helpful for thinking about this is to actually think about the classical EOMs. So another way that we could approach this problem, of course, is we could just think about the Einstein equation and the geodesic equation. And if you wanted to solve these equations of motion in a PM expansion, you would do the following. You would take the position of your black hole, expand it around a straight line trajectory, and then just have some higher order corrections. A 1 p.m. correction, a 2 p.m. correction, etc. Same thing for the metric. You'd have a 1 p.m. correction, a 2 p.m. correction, etc. And what you do is you'd sub in these power series expansions into the two equations, and then you just read off the different powers in G Newton, and you'd solve them iteratively. So for instance, if you read off the linear term in G Newton from the geodesic equation, you'd get something that looks like this. And then if you take that into the Fourier domain, the equation would take this form. And what you notice is that the thing that I'm integrating over here, Well, this is exactly the ZH vertex, which I showed you just a couple of slides ago. So another way that you can think about the WQFT is essentially solving the equations of motion. And we have a name for this in amplitudes. Of course, this is referred to as Behrens-Gill recursion. Essentially, we're running the Behrens-Gill argument backwards. In order to solve the equations of motion, you can draw a sum of tree-level Feynman diagrams. And that essentially automates the job. The reason that the WQFT is much more efficient, though, is because, as I showed you, we can write down an endpoint expression for the vertex. And we can also generalize to think about other quantities once we have that very general set of rules, which I showed you. So it turns out to be an awful lot more powerful. And this really works because, of course, the path integral localizes on the equations of motion in the steepest descent approximation, as we know. What also gets very interesting, though, when we think about the WQFT is what happens when we start comparing with tree-level scattering amplitudes. So, as I showed you, for a single black hole radiating a graviton, we remember that in this case, we have a single diagram which just corresponds to h mu nu being sourced by the leading stress energy tensor. And we can compare this with something that we would have from a scattering amplitudes perspective, in which case we would have a 3-point vertex. We would have a complex scalar and a graviton being radiated out. And the expression for that vertex has this form. But one thing that we know, one thing that's been well discussed and well understood, is that in order to take the classical limit, in an amplitudes perspective, that corresponds with taking the soft limit. So this is, amongst others, been discussed by Kosawa, Mabey, and O'Connell. What they showed is that really this k has a hidden h bar sitting in front of it, where this k bar is the wave number. And what you need to do is you need to send k to 0. And that basically gets rid of this extra term. And then what you see once we take that limit is that there's a natural correspondence. And we see that we can identify this expectation value of h mu nu in the Worldline QFT with the 3-point amplitude. So again, this is really just the simplest example that you can have, just as an illustration of how this sort of thing works. But this concept applies far more generally, and we can use it in a whole bunch of different contexts and different scenarios. So the one that we looked at, me, Jan Plafke and Jan Steinhoff, in our first paper, was we looked a lot at the case of conservative scattering. And what we found is that the iconal in the amplitudes perspective has a very natural interpretation in the Worldline QFT. In the Worldline QFT, the iconal we think of as the free energy, so the sum of vacuum diagrams. And the reason that you want to write it as a phase is simply the usual one in QFT. It's simply that you want to draw a sum on connected diagrams rather than a sum on disconnected diagrams. So from that point of view, it's convenient to package up in the form of a phase. Sorry, is somebody asking a question?
No, sorry, please go ahead.
Okay. And has been understood, so the iconal can be obtained from an amplitudes perspective by looking at the S matrix and taking this Fourier transform from the space of exchange momentum into impact parameter space. And actually in our first paper, Jan and I were actually able to derive this formula, and we were able to prove it. And the way that we did this was by using a formal understanding by thinking about a Feynman-Schwinger form of a dressed scalar propagator. Unfortunately, I'm not going to go into that today, but I encourage you to look at our paper if you're interested in exactly how all that works. What I'm going to be focusing on, though, more is the radiation. And again, the radiation has been looked at from an amplitudes perspective. And the way that the connection works for a 5-point amplitude is that the radiation can be obtained using this integral right here. And this was first understood in this paper by Luna, Nicholson, O'Connell, and White. And the way that this relationship works, what's rather lovely about the WQFT is that you can really start to understand this pictorially at the level of the individual diagrams now. So if you think about the diagrams which contribute to a 5-point amplitude in QFT, you've got, for instance, this guy right here. And you can see without even doing any work that classically this is going to map onto this diagram in the WQFT. I already showed you that this 3-point vertex maps onto this single graviton emission. The free graviton vertex is exactly the same in either theory, and the graviton propagator is exactly the same. So clearly the classical limit is just going to work. Where it gets more interesting, though, is when you have scalar propagators and how that compares with these deflection modes traveling on the world line. Because now you have a sum of different diagrams in the QFT, which all map onto just one diagram in the WQFT. And without doing the calculation in too much detail, here, what I'm trying to illustrate with these equations down at the bottom is exactly how, what I'm trying to illustrate here with these equations at the bottom is how the scalar propagators resolve themselves when you start taking the classical limit. So again, you take the limit of Q1 and Q2 being small, and you get a power series expansion like this. And this P1.Q2, it gets squared, and that's basically omega squared. That's the omega squared, which sits downstairs in this deflection mode, which travels on the world line. This leading term right here, which cancels, that's a superclassical contribution, which you get from the amplitude, and has been shown the superclassical contributions cancel out when you start thinking about these classical observed quantities. So we see how the same sorts of integrals, the same integral measure, which, I mean, if I flip back just a couple of slides, you saw exactly the same sort of structure appearing when we had these diagrams right here, but the integrals come about for a very different reason. Here we have to do an integration over Q1 and Q2 manually by hand on the amplitude, whereas in our formalism, those integrals just arise naturally from this mismatch between energy and momentum conservation. So that's the connection then to the amplitude story. So now let me proceed on and start talking about the waveform in a little bit more detail. I could also take questions at this point. It's a natural breaking point.
Question. When you write h mu nu in terms of those diagrams, the final graviton is on shell, right? It's a physical graviton of momentum K. So that should give only the radiative part of the metric, not just the full metric. Right?
Correct.
Is that correct?
Yes.
Okay, it's not a full h mu nu. Okay.
No, it's radiated. I mean, yes, implicitly you can imagine that we're contracting in with a polarization tensor on the external.
And you look at the 1/r behavior at infinity.
Exactly. That's what we do here when we look at the waveform.
Okay.
Exactly, yeah. So that's exactly what I do now is now what we're going to do is we're going to start trying to think about doing those integral, and exactly as Gabriel said, what we're now going to do is we're going to start thinking about the 1/r behavior in order to figure out what's detected by an observer who's standing extremely far away. So in order to think about h mu nu as measured by an observer, what we do is we go back and we think about the Einstein equation. And what we're essentially then trying to do is figure out what h mu nu looks like in position space. And we make a couple of assumptions. Firstly, we assume that we are extremely far away and it dies off as 1/r, so we just look at the leading term here. And secondly, we assume that we emit our graviton with some fixed energy omega. And in that case, the form of h mu nu takes this particularly simple form, where s mu nu is precisely this thing which we were able to calculate using the WQFT. K, however, is no longer just an arbitrary vector, form momentum vector. Rather, K is now a vector which points directly from the point of scattering to us, the observer. So rho is a unit vector, x is the unit vector pointing towards us, the observer, and omega is the energy of this emitted graviton. So S mu nu, essentially, we can already think of this in some sense as our energy or frequency domain waveform. And we had a talk on this by Massimiliano Riva, who had a paper on this subject just a few weeks after we had our paper dealing with the waveform. And they were looking at this thing in the energy or frequency domain. We, however, found that it was quite convenient to look at this thing in the time domain. So in order to get the waveform in the time domain, we take one extra integral, which is the integral over the energy of the emitted graviton. And what we find then is that this k dot x, you can naturally interpret it in terms of the retarded time. So essentially then what we end up doing is basically just a Fourier transform, taking us from the frequency domain into the time domain. And the waveform that we're looking at depends on u, the retarded time, as well as theta and phi, which are the angles towards the observer, which I'll define in just a moment. What we also then do is we break this thing up in a PM expansion. So we have Fij, which is summed in different powers of g Newton, and we're going to be interested in the 2pm component of this thing. Finally, what we generally do is we place this thing on a basis of polarization tensors. And for convenience, we make use of the purely spatial plus and cross polarization tensors. And we can always obtain these plus and cross components from the full waveform simply by contracting them in exactly this way. So what the calculation boils down to then is we had our expectation value of h mu nu, which had these integrals I already showed you. And now we need to do one more integral, which is we need to do this integral over the energy of the emitted graviton. So ignoring the full details of the integrand, this is now what our integration measure is going to look like. So you see we have the same delta functions we had before. We've got the same q1.b1, q2.b2, and we have this extra component here. And the reason that this omega integral turns out to be so useful is because it actually allows us to resolve all of our different delta functions. Essentially what happens is there are three energies here. There's the energy emitted by black hole 1, the energy emitted by black hole 2, and the energy radiated out to infinity. And we now have three delta functions, so we can now resolve all three of them because we're conserving energy on each of those two world lines. And once you resolve all of these different components, it then turns out that you actually only have to do a three-dimensional Euclidean integral over vector q, which is the momentum being exchanged between the two world lines. Rho.v2 is just this commonly occurring factor, which comes about from Lorentz transformations. And what we find is this, this vector b tilde, which I'll talk more about in just a moment. Now, what turns out to be quite helpful at this point is to pick a frame. And rather than working in the center of mass frame, as one might expect, it turns out that it's easier to work, in this case, in the frame of one of the black holes, so black hole 1. So in that case, what we do is we take v1, the velocity of the first black hole, to just be, purely time-like unit vector. And then v2 has this form just to ensure that v1.v2 gives gamma. And then also without loss of generality, we choose b1 to be 0. So we basically just fix our coordinate system so that it sits on top of the first black hole. And then our coordinate system is set up such that the x direction points along the direction of this velocity, the y direction points along the direction of the impact parameter, and z is orthogonal to the plane of the scattering. For now, because we're looking at the non-spinning case, the scattering is occurring in a plane, and the z direction is orthogonal, so that's where we're going to radiate angular momentum. And as I say, these delta functions allow us to fix these various components right here. And for instance, this is the value of omega, which we find. One thing that we didn't talk about in our original paper is exactly what the precise interpretation of this b tilde is. But we do now understand this thing a little bit better. This shifted impact parameter makes a bit more sense when you look at it in 4 dimensions. And actually, Kovacs and Thorne talk about this in their original papers. What you can think about is you can sort of imagine that you had the impact parameter, and if you sort of imagined it continuing, like if the black holes didn't, talk to each other, so you've got the proper time for black hole 2 times the velocity of black hole 2 minus the time for black hole 1 times the velocity of black hole 1, then this is how it would evolve. And this b tilde then is simply obtained by taking the 3-dimensional part. U then is the proper time as measured by each of the 2 black holes. So because we're working in the frame of black hole 1, U1 is just equal to U. But if you take U2, then of course that has to be given by a transformation. And that's what gives rise to this expression right here. And this b tilde actually crops up again and again, quite interestingly, in these calculations. How am I doing for time, by the way, Justin?
So I think you have another 30 minutes, including questions.
Ah, okay, great, perfect. Okay, so we then start to take a look at the integrand and what the waveform looks like exactly. And once we've done this procedure of getting rid of our delta function constraints, going into the rest frame of the first black hole, our integrand looks like this. And as I showed you, we had 3 diagrams. What's convenient about working in the rest frame of the first black hole is that this diagram actually vanishes in this frame, because it turns out that it's overall proportional to V1, which in this frame is purely time-like, and we contract with the polarizations, which are purely space-like. So it actually just gives 0. So that's useful. It means we can just drop one of the diagrams. And the propagator structures of the others are kind of as follows. So you can think of this Q squared as kind of being like a Coulomb potential, which you get from the first black hole. And this Q dot E1 is the propagator for the Z particle traveling along. For the other one, you've got a Coulomb potential being produced by the first black hole. You've also got a Coulomb potential from the second black hole. But of course, because we're in the frame of the first black hole, it's going to have to be related by a Lorentz transformation, which is this basically what this L matrix is doing for you, which you can derive. And I'm not going to go into too much detail about how these integrals are actually done. You'll have to look at the paper for that. But what we do is we then perform these integrals and we obtain the waveform. And over time, we've started to understand a little bit better how one is supposed to write these things. And once you know more about the shifted impact parameter, you start finding out what the best language is. So here we've got this b tilde squared. So that's the 4-dimensional shifted impact parameter squared. Here we've got the 3-dimensional part of it, the mod. And here we've got a Lorentz transformation on the 3-dimensional part. So we've got this U1 and U2, the retarded times with respect to each of the 2 black holes. Alpha, alpha prime, beta, and beta prime are some coefficients which just sit on top of these things. And these things depend on the mod of the impact parameter, the relative velocity, the 2 angles, theta and phi, and the retarded time. So just to give you a couple of examples so you can see roughly what the result looks like, here the simplest ones are alpha prime in the plus and the cross polarization. So this just gives you a rough idea of what these things are. And rho dot v2 we can also write in terms of these very same variables. And this, as I said, this agrees with the seminal result from Kovacs and Thorne from the 1970s. And in order to show you even more what this thing looks like, we actually have a visualization of the waveform. So let me switch over now to here, and let me show you this thing. Whoops. Yeah. So this is the F plus component as a function of theta and phi as it evolves over the time domain. See, so I'll just run that one more time. So just to demonstrate that we know what this thing is, and we have a similar little plot from for the cross component, and it looks similar. So now let me move on a little bit further, and let me talk about some other quantities which we can obtain by thinking about this thing. The first is we can think about the radiated angular momentum. So this was also discussed by Massimiliano yesterday, and to obtain the total radiated angular momentum, you can use the following formula. And the only component which is relevant in the non-spinning case is the z direction. The leading order waveform F1 actually doesn't depend on the retarded time, so you don't need to take the time integral. And what happens is you find that the radiated angular momentum only depends on the 2 p.m. wave memory, which is the difference between the waveform at time t equals plus infinity and time t equals minus infinity. And in that case, you actually only need a single diagram in order to describe this thing, which is the diagram where we have one of these deflection modes propagating along the second world line. What this does is this confirms a claim which Demetrius made, which is that the radiated angular momentum doesn't actually depend on the bulk interactions at this order. And if we perform the relevant integrals here, then we're able to reproduce Demetrius' result, which is that we have the ratio of the radiated to the initial angular momentum, which depends on this universal factor here, which includes this arctange of V. What's nice is that even though we're working in the frame of black hole 1 rather than the center of mass frame, we actually get exactly the same result anyway. And the reason is because the difference in frame corresponds simply to an overall factor which cancels out when you mod out by the initial angular momentum. And as I say, this was also discussed in this other paper, which came out a little bit after ours. The other thing that we looked at is the radiated energy, but has also been commented. When you start from the integrated waveform, it turns out to be a little bit more difficult to obtain this. So we end up working in a post-Newtonian expansion. So to seek the radiated energy in the frame of black hole 1, we dot this thing in with V1. And for instance, we can obtain the energy spectrum. So dE by d sigma, where sigma is the solid angle over which we're integrating. So to do that, we have to take the time derivative of Fij, square it, and integrate over the proper time. This is quite difficult to do in a PM expansion, although not impossible, given that the PM result is known. But in a post-Newtonian expansion, it's quite straightforward. And just to give you an example of what this thing looks like, this is the leading PM result for the energy spectrum, which was also produced in the paper of Kovacs and Form. We in our paper have now written this thing down up to order v cubed. However, it's very straightforward to go to as high orders as you need. And then finally, if we do the integration over the solid angle over theta and phi, we can then reproduce the total radiated energy, which again, it's this expression which we can go to as many orders in post-Newtonian as we need, but the post-Minkowskian result is known. So this was this work by Hermann, Paramartinez, Ruf, Mao Zeng from earlier this year, where they used the KMOC in formalism in order to get this thing in a post-Minkowskian expansion. It would be very nice to be able to reproduce their full result using this technology, but unfortunately, we haven't yet quite figured out how to do that. So that's as much as I wanted to say about the non-spinning case. So now let me share with you some of what we've been doing in the spinning case. So to begin my discussion of spin, let me tell you a little bit about this rather beautifully named paper, Susie in the Sky, by Gibbons, Ritschik, and Van Hulten from '93. And what they showed, well, what was already known, is that the Dirac theory of a spin 1/2 fermion can be described by this n=1 supersymmetric theory on the world line. So in order to represent the spin of a particle of a world line, you can introduce this Grassmann valued spinner, where this capital D by d tau is a covariant time derivative on the world line. Of course, these A are local frame indices, so in order to describe this thing, we now have to introduce a Vielbein, so we have E mu A in the following way. And psi is a real Grassmann valued spinner. And as has been shown, this theory is rather beautiful. It enjoys an n=1 supersymmetry. It is invariant under the following shifts. And amongst other things, what Gibbons et al. Talked about in their paper was how we can use this to think about a spinning particle. And the way that we can think about the spin tensor is we can interpret it as an outer product of these Grassmann valued spinners. So the antisymmetric nature of S mu nu comes about simply because these psi's are Grassmann valued. And this S mu nu is, of course, related to the Pauli-Lubansky spin vector. What's really quite elegant about this, though, is because this theory is supersymmetric, we have conserved charges. And these are H, which corresponds to energy conservation, Hamiltonian, and Q. And Q, it turns out, takes this form. And if you just contract in with another psi, you find that this conservation of supercharge is precisely equivalent to what we, in a perhaps more conventional language, would think of as the spin supplementary condition at this order. Now, in order to show that this actually allows you to describe a spinning particle, what you need to do is you need to look at the equations of motion. So in this case, the spin, the Grassmann value spinner is simply parallel transported along the world line. And the geodesic equation for the position x picks up this term here, which can quite easily be transcribed to be written in terms of the antisymmetric SAB. And these, at linear order and spin, are precisely the Matheson-Papapetrou spin equations. So this is a very nice, elegant story, and it shows you that you can use a Grassmann-valued spinner like this to help you describe spin. Unfortunately, this story stops at linear order and spin, and what we'd like to do is go to higher orders. So the question is whether we can generalize this theory. And the answer is we can. It turns out that there is an n=2 extension of this theory, which was written down by Bastianelli, Benincasa, and Giombi in 2005. And what they did is they generalized this theory to a complex valued spinner. So we have a theory which looks like this, where psi is now complex and it has a psi bar, and this thing now enjoys an n equals 2 supersymmetry. And again, we identify the S mu nu in precisely the same way. And the claim now is that we can identify it with the spinner using a psi bar and a psi in this way. So one quite easy way that you can use to convince yourself that this definition of spin is sensible is you can look at the Poisson bracket. So in a first order formalism, you have these graded Poisson algebra between psi bar and psi. And you can very quickly show that that gives rise to the usual SO1 free algebra for the spin tensor. What's especially nice, though, is how this supersymmetric story continues and gives us even more supercharges. So again, we have energy conservation being respected on the world line. We now have these two supercharges, fermionic supercharges, which give rise to the spin supplementary condition. And finally, psi bar dot psi has to be a constant. And this, in another language, we might think of as the fact that the preservation of the mod of S mu nu along the world line. That's not a rigorous argument. In order to fully prove that this is equivalent, you need to look at the classical equations of motion and show that they reproduce the Matheson-Papapetrou equations at order spin squared. But that's just a little primer into how this works. So when we now move to extend the Worldline QFT to include spin, what we now essentially do is we take our partition function as including this this new spinning action. The other thing that we can do is that we can start to include some spin-induced multipole moments of this form right here, where we have some Wilson coefficients, CE. But the trouble with these terms is, as far as we're aware, these have the property that they break the n equals 2 supersymmetry. So it would appear that this supersymmetry is a property which is special to the Kerr black hole. I mean, that's what we think, that's what we believe. The procedure then for using the WQFT formalism is we expand the position of the black hole around the straight line trajectory, same as before. We expand the spin, but now we also expand the spinner around a background value of the spinner plus a perturbation. And we do the same thing with the spin tensor, which we can now think of as a composite field built out of as an outer product of these spinners. So the constant piece of the spin tensor comes from the outer product of psi bar and psi. And then, of course, in order to write down the rules, we have to expand the Vierbein as a power series in h mu nu, the gravitational field. And then we do exactly the same as we did before. We work in momentum space. We write down Finemen diagrams. We write down Finemen rules. The only difference from before is that now we have a new field. Justin, how am I for time?
So I would say 17 minutes, including questions.
Okay, I think I'm nearly there now. So when we have the Finemen rules, which now include spin, we need to think about the fact that the existing Finemen rules, which we already had in the non-spinning case, now also need to get modified. So on this slide, I'm ignoring these spin-induced multipole moments. And for instance, if you think about the leading term, where you just have a single graviton being radiated from the world line, you now pick up these extra terms which come from the constant piece of the spin tensor. And if this thing looks rather like an exponential, well, it should, because one thing that's well known is that the linearized stress energy tensor for a spinning black hole has an exponentiation, which has been shown by Guevara, Okarov, and Vines. And we see that reflected in this Finemen rule right here. Similarly, we also have the Finemen rule with a single deflection mode on the world line, which again picks up these corrections which involve the constant piece of the spin tensor. But now we have some new kinds of Finemen rules which also enter the game. For instance, we can now start transmitting one of these spinners along the world line. And we have a new Finemen rule which is associated with the existence of this spinner. And you see we now have one of these Grassmann spinners dangling on the external index. We also find now that we can start emitting multiple gravitons from the same point on the world line. So that rather nice property I showed you in the non-spinning case, where everything was linear in h mu nu, unfortunately that no longer works once you include spin. Again, we use retarded propagators both for the z deflections and for the spin components. So now we have our 1 over omega squared propagator for the z's, and we have a 1 over omega propagator for the spin. Bear in mind that the direction of this arrow doesn't have to correlate with the I epsilon prescription. The I epsilon prescription tells you about causality. The direction of the arrow tells you about psi bar, which is a different thing. You can have both. So, obviously we can do a lot with these rules, but for today, I'm just going to settle for looking at the Bremsstrahlung at order s squared. And of course, the integrand is very similar to what we had in the non-spinning case. So we have the exact same two kinds of diagrams as we had in the non-spinning case. But obviously we have to modify the Finemen rules for the inclusion of spin. But now we also have two new kinds of diagrams. So we've got a 2-graviton interaction on the world line, and we can also now start propagating one of these spinners along the world line as well. In the case of this diagram, it comes twice. The spinner can go left and, sorry, it can go right, it can also go left. When we add up all the contributions, we find that the integrand takes a very similar pattern to what we had in the non-spinning case again. The only difference now is that we find that we have higher powers of the exchange momentum in the integrand. So the whole same analysis I did with this shifted impact parameter, it all works exactly the same. All the arguments go through. And you find that you have these higher order powers in Q, which correspond to these higher order spin corrections. And in practice, once you know how to do the integrals in the non-spinning case, it's not too hard to generalize to spin. Essentially, all you need to do is you just take derivatives with respect to b tilde, and that allows you to pull down more powers of Q, which you put in your numerators. And so you see then that the final form of the waveform, well, obviously these coefficients can be quite complicated because there's a lot of variable dependencies, but you see that you start ending up with more powers of the impact parameter showing up downstairs in the waveform. And that's characteristically how this thing starts to look like. So obviously the waveform is quite large, so I'm not going to be able to present it to you entirely. So the way that I'll therefore conclude is I'll go back to looking at the radiated angular momentum, which I showed you in the non-spinning case. And we can use the exact same formula to compute it in the spinning case. However, because our scattering is no longer happening in a plane, what we now find is that we're going to radiate angular momentum in different directions. We're going to radiate in two directions, the z direction and the y direction. But what we found is that it's quite convenient to package them up into this complexified form like this. And after integration, we find that we can write down the radiated angular momentum in this form. So in order to express the final result, what I've introduced are the Pauli-Lubansky spin vectors, which exist in their own respective rest frames. So because we're in the frame of black hole 1, A1 is purely spatial, but A2, of course, because we're working in the frame of black hole 1, it has to be related by a Lorentz transformation. And A3 is simply given as the sum of the two spin vectors. And so we see that we actually, again, have quite a nice form for the radiated angular momentum. And this factor I, which includes this arctange, it seems to be fairly universal. And it crops up again even once we include spin interactions, which is quite interesting. So, I mean, that's as much as I'm going to say for today. I mean, hopefully I've convinced you that this WQFT is shaping up to be quite a powerful tool for classical two-body calculations. And what we've now shown is that it has a natural extension with supersymmetry. When we start including that SUSY extension, we take our Z deflections, H mu gravitons, and we also include the spinner now, and that propagates on the world line. And we have this issue that because we're only conserving energy on the world line, that means that we can get loop integrals in some sense, while we're only actually looking at tree-level diagrams. In our previous paper, we obtained the 2PM waveform and reproduced the result of Kovacs and Thorne. We got the radiated angular momentum, reproducing Demetrius, and the radiated energy spectra. And now what we're doing, and we're hoping to put this out within the next couple of weeks, is the waveform generalized up to order s squared, including the radiated angular momentum, as I showed you. But hopefully I've convinced you that this technology can be used for a lot more things, and we're really just scratching the surface with spin, I think. One thing that I didn't mention is we actually have already been able to compute the 2PM deflection using those exact same set of Finemen rules, which reproduces work by Leo, Porto, and Yang, and also Cosmopoulos and Luna from earlier this year. But I think even beyond the physical observables, I think there's a lot more to be understood here. Basically, what we're looking at is a whole class of 1D supergravity theories. And I would be very curious what this has to say about higher spin and how we can connect this to the amplitude story that people are working on. Yeah, so I think that's all from me. Thanks very much.
Thank you, Gustav, for the great talk. And once again, we have our first hand up from Julio. Go ahead.
Hi, thanks, Gustav, for a nice talk. So I have some questions about these supersymmetric actions that you were writing.
Yes.
So I have two questions. So the first one is, in higher dimensional sigma models, or things like sigma models, typically imposing supersymmetry tells you that the target space has to have some special kind of geometry, like n=1 or n=2 SUSY. They tell you that it has to be Kähler or hyperkähler or something like that. When you impose enough SUSY, there's some restriction. So I was wondering if here, because you're in 1D, you can avoid that. And the other question is, when you wrote the higher dimension operators to call the tidal deformations, presumably all of those won't be allowed by SUSY. So does SUSY tell you that only certain ones are allowed, or?
Yeah, exactly. And this is something that we've been thinking about. Yeah, it's a really good question. So basically, there's a whole family. So if you don't couple to gravity, there's basically what these authors have shown is that there's a whole family of these theories, actually for arbitrary numbers of supersymmetry. Basically, what you do is you just keep adding more and more flavors of this spinner. The tricky part is coupling them to gravity. n=2 is the highest amount of supersymmetry that has so far been successfully coupled to gravity. But as far as we're aware, this form of the action is unique. And so adding this spin-induced multipole term would appear to spoil the supersymmetry, we think. So what that suggests is that the supersymmetry is specifically a property of the Kerr black hole, which is interesting. Because I think other people have remarked that Kerr seems to have certain special properties.
But excuse me, this supersymmetry is a supersymmetry on the Worldline.
Yes.
Nothing to do with space-time supersymmetry.
Right. Yes. I mean,
you're not describing a multiplet of a supersymmetric multiplet.
No. This is a physical theory I'm describing. This is not like doing n=8 supergravity. This is a physical theory. It exists only on the Worldline.
But presumably, if you want more supersymmetry on the Worldline, then you will need to add more supersymmetry in the target, like more stuff in the target space.
What you need to add is more of these spinners on the Worldline. That's what you need. So you saw that in the n=1 case, we had just a real spinner. Another way to think about n=2 is you could think of it as two flavors of real spinner. That would be another way to describe it. To get more supersymmetry, you need more.
And why do you need supersymmetry?
Well, because, you don't, but it appears to be very much the right thing to do. The supersymmetry appears to go hand in hand with the spin supplementary condition. The conservation of supercharge is related to conserving, is related to the SSC, as we can see.
So
just one comment, maybe.
Yes, please.
So this has been generalized to n=4 supersymmetry as well, but then you cannot couple to a generic space-time background. Then it has to be an Einsteinian manifold. I mean, in that sense, you're absolutely right, Rudi. But that's how far people have gone so far.
Yeah. I'm sorry, I actually can't see the questions at the moment for some reason.
That's okay. I guess if that was all from Jan, next we have Demetrius.
Hi. I was wondering on this slide, actually, this supersymmetric charges that are conserved, they seem pretty generic. They seem that they should hold even if you're not talking about a black hole, Kerr black hole. So it's a little puzzling that when you add the when you go away from the black hole because you break supersymmetry, I would expect they are not conserved anymore, or am I wrong?
Yeah, I mean, it's something that we've been thinking a lot about as well. I mean, certainly there's nothing to stop you from just adding a term like this on your action, thinking about the equations of motion, and then just saying, right, I'm going to demand that these things, I'm going to demand the SSE anyway. I mean, indeed, this is what people do, of course. However, as far as we're aware, the manifest supersymmetry property of the action, basically the guarantee of this thing, is lost. You know, what consequences that exactly has, we're not entirely sure of at the moment. However, what we have done is we have added this thing to the action. And as I say, we have so far computed the 2 p.m. deflection using the same set of Finemen rules, and we have reproduced the results of Rafael Porto and others. So we are nevertheless quite confident about this thing, but as I say, there's a lot still to be explored here. It's very early days.
So on cell, like on the equations of motion, you managed to maintain the conservation of the charges.
Yes.
Oh, that's great.
Okay, Thibault, please go ahead.
Yes, you mentioned angular momentum loss in the spinning case, but you computed that in the rest frame of one of the particles, because you know there are issues about the meaning of angular momentum loss versus the K, the boost constant loss. So what is the meaning of this? Did you compute it in the center of mass frame too?
No, it's the frame of black hole 1.
You should compute it in the center of mass frame to see.
Okay.
Okay, it was just a remark.
But we're working on this. I mean, we have to understand the boost component, as you say, Thibault.
Yeah.
Indeed, then we can do the transformation.
Yes.
Yeah, I think that even if you want to get to the center of mass frame initially, it's always easier to do the integrals in the frame of black hole 1. I think you probably want to transform it afterwards that's probably what I would go for.
And okay, next we have Rodolfo.
Okay, yeah, thanks. A curiosity, did you try to go beyond the G-squared term for the radiated momentum? And just, I mean, you seem to have a formalism that, okay, would allow you to just continue.
I don't think I understand the question. So,
right, in the question here, you write plus OG cube. Did you try to calculate that?
Oh, for the radiated angular momentum?
Yeah, for the radiated angular momentum, yes.
Oh, no, because for that we would need the higher order components of the waveform. We would need the 3 p.m. part of Fij.
Okay, yeah, just a curiosity. And maybe just linking with the question Thibault had about the center of mass, you mentioned that you are thinking of just doing the Lorentz transformation on the final result and finding the center of mass expression for the is that what you had in mind?
Yes.
Yeah. Okay.
But there are issues about the meaning and definition. Okay, there are ambiguities.
I mean, I think he's thinking just to do the transformation on the waveform, not on the angular momentum. That is what I was asking.
That may also be true. Yes, that could be another way to proceed in this case. I mean, the reason that I say that it's easier to work in the frame of black hole 1 is simply because these integrals, you want this to be Q squared rather than some matrix inside of Q like we have here. That's really all it is. It's just a matter of convenience for doing the integrals.
Yeah, I mean, I'm just asking because as Paolo was showing yesterday, we have the expression in the center of mass frame, right? Just for habit, we are deriving in that framework, and we would be very interested, of course, in comparing, but it's not immediate, right? So once you have the expression in the center of mass frame, we would be very interested to see them.
Okay.
Okay, I think we have time for one more question.
Yeah, I just want to add a very small comment. We have computing basically the same thing as yours, like the waveform. And yes, we in the paper we report the waveform in the rest frame of one of the two particles, but we have computed the pseudo stress energy tensor in a generic frame, so we can actually provide you with the expression for the waveform in the center of mass, and it's just a matter of writing it out nicely. I think in the next days we will probably have.
I'm sorry, are we talking about the spinning case here or the non-spinning?
No, the non-spinning case.
Non-spinning case, okay. Okay, thanks.
Okay, and then actually very last question from Paolo.
Just a comment. In the 70s, this wall sheet supersymmetry were used for computing string amplitudes. And for n equal 1, you get Neves-Schwarz model. For n equal 2, you get what is the n equal 2 model, which the idea was to go down in dimension from 26. But for n equal 2, you get 2 dimension, and for n equal 4, you get minus 2 dimension.
Mm-hmm.
Using exactly the same algebra.
But that was with strings.
That was done for string, yes.
So
you can take the zero slope limit and you get a...
Not a word line theory, a word sheet theory.
Yes, exactly, yes.
There are extra constraints in that case.
I mean, I think it's certainly true that everything we're doing has a very stringy sort of nature to it. You know, it's a world line rather than a world sheet, but it's very much the same sort of approach one takes in string theory, coupling, you know, spinners to the world line in this case.
Yeah, but in string theory, you have to kill the, you know, the anomalies, and this gives constraints.
Mm-hmm.
Even in flat space time, you know, you have critical dimensions and so on and so forth. If you have a point particle, I think the constraints are less severe.
Yes, that's why the critical dimension for the n equal 2 string is 0. I mean, sorry, is 2.
2, yeah.
That's sorry. And then it's minus 2 if you have an n equal 4 supersymmetry.
Whatever that means.
Yes, whatever that means, yes. I have another question. If you take, you have S mu nu.
Yeah.
This form of S mu nu was used also in the 70s to get the Lagrangian for spin-a-half particle. And if you take S mu nu square, don't you get 0 if they are anti-commuting variable?
Well, naively, no, because there are 4 different components.
For n equals 1, yes, but not for n equals 2.
Yeah, right.
N equal 1, you get 0, yes. In fact, the fact you get spin-a-half is because you have to do the quantum theory. So the psi doesn't anti-commute anymore, but the commutator is 1.
Exactly.
Yeah.
And this is why, if you look at the spin 1/2, this only gets you as far as linear order in spin, the dipole in the classical theory. So of course, if you want to do more than that, you have to go to, you know, massive spin 1, for instance.
So the total spin is linked to the U1 charge of n equals to 2 Susy algebra. Through the S squared condition.
Okay, then thanks again